Hello there. My name is Mr. Ahmad Al Ghul. I'm gonna be your chemistry teacher, inshallah. Today, as we discussed in the last session, we're gonna talk about chemical equilibrium. It's Saturday, September 6, 2025. When we say equilibrium, we're gonna have, let's say, two things. We're gonna have like balancing between two processes. So we're gonna have an equilibrium. Something is going up or something is going down at the same time, or something going right and then something else is going left at the same time. This is the meaning of equilibrium in general. But before we going deep in our chemical equilibrium session, we just go back to our previous session and discuss about reaction. In our previous session, we say that we're gonna have a reaction. Each reaction will have reactants and will have products. This reactant is suppose we have A react with B, then we're gonna yield C and D. But before having C and D, or in order to have C and D, A and B must collide. So first they must collide, and secondly they should collide in a proper orientation or favorable orientation. So the first A should collide with B, and second they should collide in favorable orientation, correct? Third, this collagen, or this, let's say, this collagen and favorable orientation should have with enough energy. So we're gonna have enough energy. If we have these three conditions, then we're gonna have a product. So A will react with B, collide in favorable orientation and with enough energy. After that, we're gonna have the product, which is C and D. But suppose someone will ask, if C and D collide with each other and in favorable orientation with enough energy, can we have A and B again? Yes, we can. So this is gonna be the forward reaction, and this is gonna be the reverse reaction. So we have two reactions. One is going to the right and the other is going to the left at the same time. So we have double arrows, and this is the meaning of equilibrium. Let's go. Our objectives for today: one, defining chemical equilibrium. What is the meaning of chemical equilibrium? And when we say chemical equilibrium, it's the meaning of what in, let's say, in the name of chemistry. Then we should explain the nature of equilibrium constant. So for any chemical equilibrium, we're gonna have something called equilibrium constant. After that, we're gonna learn, inshallah, writing the chemical equilibrium expressions and carry out calculations involving these chemical equilibrium expressions. Three things we're gonna learn today. Okay, let's go. One, when we say reversible reaction, that's the meaning of we have two reactions at the same time. We're gonna have a forward reaction and we're gonna have a reverse reaction. If we have both at the same time, this is the meaning of a reversible reaction. Theoretically, every reaction can proceed in two directions. So any reversible reaction should be in two directions. One is gonna be the forward, which is going forward, and the reverse reaction was going back. When we say forward, its reactants would give me products, and when we say reverse, products will give me again reactants. Essentially, all chemical reactions are considered to be reversible. under suitable conditions. So all chemical reactions are considered to be reversible. But if we have the suitable conditions, yes. If there is no suitable conditions, no. A chemical reaction in which, this is the definition, a chemical reaction in which the products can react to reform the reactants is called a reversible reaction. So, any reversible reaction is a chemical reaction, and in this reversible reaction, the products will react with each other and will reform the reactant. Okay, so these products here, okay, the reactants will react with each other to give me the products. Then our products will react with each other again and give me reactants. In this case, we're gonna have a reversible reaction. Great. A reversible reaction is a chemical reaction is in chemical equilibrium. So when we say equilibrium, the meaning of equilibrium in chemistry, it's about rate. So the forward reaction will have a rate and the backward or the reverse reaction will have another rate. If these rates are equals, then we're gonna have a chemical equilibrium. So I want to put an equal sign beside chemical equilibrium. Why? Because the rate of reverse reaction, okay, and the rate of forward reaction should be what? Should be equal. And the concentration of its products and reactants will remain unchanged. So the rates are equal and the concentration are unchanged. Okay? So as a state of dynamic equilibrium has been reached when the amount of products and reactants remain constant. Okay? When we have a state of equilibrium, we should have the amount of products and the amount of reactants should be constant. The amounts. Okay? But the rate should be equal. Both reactions will continue, but there is no net change in the composition of the system. Okay, this is clear. Okay, the chemical equation for any reaction at equilibrium is written using a double arrows, and well, that's what we start with. We start with double arrows. Okay, so these double arrows means that we're gonna have equilibrium. Okay, and this reaction is reversible reaction. For any reversible reaction, we have a state of equilibrium, but directly when we have double arrows, we having an equilibrium and we having a reversible reaction. So if we want to describe this reaction here, we say that the forward reaction, the mercury oxide is decomposed to mercury and oxygen. Also, oxygen will react with mercury to give me mercury oxide. Good. So here we have forward reaction, this one here, and we have another reaction which is the backward reaction. Those both with each other will have a reversible reaction. Many chemical reactions are reversible under ordinary conditions of 1. Temperature, 2. Concentration. Okay, so these chemical reactions will be reversible if we have an ordinary conditions of temperature and concentration. They will reach a state of equilibrium unless, at least, we're gonna have an equilibrium unless, okay, at least one of the substances involved escapes or removed from the reaction system. So if we have an equilibrium, a reversible reaction in an equilibrium, this will be, let's say, continued. But if at least one of these substances escapes from the reaction system or removed from the reaction system, this equilibrium will stop. When the products of forward reaction are favored, there is higher concentration of products than reactants at equilibrium. So if we have a reaction and here we have the reactants and here we have the products, and the concentration of products higher than the concentration of reactants, this means the equilibrium will go to the right more. Going to the right more. Well, that means it's going to be the equilibrium lies to the right. And if we have the opposite, here's the opposite. When the products of reverse reaction are favored, what are the products of reverse reaction? Those are reactants already. So reactants, here is the products, but we have equilibrium case, but the reactants are higher than the products. This will lies to the left. So it's about concentrations. Higher the concentrations of reactants, this means the equilibrium going to the left. Higher concentration of products, this means the equilibrium is going to the right. Great. But if we have equal amounts, this means that neither reaction is favored. In other cases, both forward and reverse reactions occur at nearly the same extent before chemical equilibrium is established. Neither reaction is favored, and considerable concentrations of both reactants and product are present at equilibrium. This is before. Okay, let's see. Here, as you see, the bigger arrow is going to the right. This means the equilibrium is going lies to the right. But here we have the opposite. That means it's going to be lies to the left. Neither reaction is favored when you have equal amounts or concentrations of products and reactants. As you see, the two arrows with the same size. Here we have the two arrows at the same size. Good. Okay, now we're gonna discuss the equilibrium expression. We know what's the meaning of reverse reaction and the meaning of chemical equilibrium. Now we're gonna talk about the equilibrium expression or equilibrium constant. As you see, here we have A and we have B will react with each other, will give me C and D. As you see, there is amount of A called N, and there is amount of B called M, or a concentration of B, and here is the concentration of C and the concentration of Y. Initially, reactants are maximum and products are zero. At the beginning or the start of any reaction, we're gonna have A and B, whose the reactants are in the maximum, but we have 0 C and D at any start of any reaction. Over time, the rate of forward reaction will decrease, correct? As A and B are using up, we are using A and B, so the rate of forward reaction will decrease. And in the opposite of that, the rate of the reverse reaction will increase as C and D are formed. Okay, when we gonna have an equilibrium state? When these two reaction rates become equal. Here, equilibrium is established. So, the question now, when we're gonna have an equilibrium? We're gonna have an equilibrium when we have a forward reaction with equal rate of a backward reaction or reverse reaction. In this case, it's called equilibrium or chemical equilibrium. As you see, A and B will give me C and D. This is the forward reaction. As you see, at the beginning of reaction, it's gonna be the maximum point here, and the rate will decrease. And the reverse reaction, which is C and D, will react with each other here to give me A and B, and the rate will increase by time. Here is the reaction rate. Then the forward rate will equal the reverse rate. At this case, we're gonna have equilibrium. At this case, we're gonna have the equilibrium. Again, when we're gonna have the equilibrium? When the forward rate equals the reverse rate. But as we going with the reaction, the forward rate will decrease and the reverse reaction rate will increase. When they are equal, we're gonna have the equilibrium between A and B, C and D. Okay. After the equilibrium is reached, the individual concentration of A, B, C, and D undergo no further change if conditions remain the same. If there is no change in conditions, a ratio of these concentration or their concentrations should also remain constant. The equilibrium constant is designated by the letter K. Designated by the letter K. So when we say equilibrium constant, we will have K. K, it's about concentrations. So before we are writing K equal the concentration of products, when we have the products are here, over the concentration of reactants. Concentration of reactants. So K equal concentration of products over the concentration of reactants to the power of coefficients. To the power of coefficients. As you see, this is the concentration of C multiplied by the concentration of D. Concentration of C is to the power of X, which is the coefficient of X. And here we have D to the power of Y, which is the concentration of, or the coefficient of D. The same for A and B here. So this is the general formula of writing concentration of, this is the general formula for writing the equilibrium expression, and we called it K. Okay? Okay. When we talk about concentrations, we're gonna have three scenarios. Scenario number 1, scenario number 2, and scenario number 3. Scenario number 1, if the concentration of products equal the concentration of reactants, okay, in this case K will equal concentration of products over the concentration of reactants, and since they are equal, K will equal 1. So if K equal 1, this is the meaning of concentration of products will equal the concentration of reactants when we have equilibrium, and when we have equilibrium, when we have equal rate. Remember that equal rate meaning we're gonna have equilibrium. Case number 2, if the concentration of products over than or higher than, bigger than concentration of reactants, in this case K will equal concentration of products over the concentration of reactants, and in this case K will be more than 1 because concentration of products is bigger than or higher than the concentration of reactants. Third case, which is the opposite, concentration of products less than concentration of reactants, and in this case K will equal concentration of products over concentration of reactants, and K will be less than 1. These are the only three cases we're gonna have. Concentration K will equal 1. This is the meaning of equal concentrations of products and reactants. If K is more than 1, this is the meaning of concentration of products higher the concentration of reactants. And if K is less than 1, we're gonna have more products, less products than reactants. And this all is written here. Okay, the constant K is independent of the initial concentration. Why? Because the initial concentration is the maximum of reactants and zero concentration of products. So at the beginning of the reaction, there is no equilibrium already. But K is dependent on the temperature of the system. So changing the temperature will change the equilibrium expression. Changing temperature will change what? K. Any change in temperature, there is a change in K. Okay. The numerical value of K A particular equilibrium system is obtained experimentally, for sure. In chemistry we have experiments, that's what we do it. If K is equal to 1, there are roughly equal amounts or concentration of reactants and products. And if the value of K is smaller than 1 or small, the reactants are favored. And a large value of K or higher than 1 indicates the products are favored. Great. Only concentrations of substances that can actually change are included in K. So anything can actually change, we will include it in K. Pure solids, pure liquids are omitted because their concentration cannot change. Why? Because there is no change in the pure solids amount and pure liquids amount. Here, how to write or determining K equilibrium is, for sure we should write a balanced equation, chemical equation, okay, and we should have an equilibrium for sure. Then to write the expression, place the product concentration in the numerator, sure, and the concentrations of reactants will be in the denominator, correct? So product over reactant concentrations. Okay, for reaction occurring in aqueous solution, water is omitted because the concentration of water almost constant during the reaction. Then complete the equilibrium expression. To complete, we should raise each substance concentration to the power equal to the substance coefficient. So here X and Y. Great. So K is a ratio between products and reactants. The mathematical product of concentrations of reactant substances. Each concentration is raised to the power equal to the coefficient of substances in the chemical equation. No need to remember that. There is a need to understand that K will equal concentration of products to the power of the coefficients over the concentration of reactants to the power of reactants coefficients. Okay? Okay, let's see some examples here. Some examples. As you see, here we have the reactants and here we have the products. Okay? Reactants and products. Here. As you see, here we have 2, so here we have 2. Here we have 3, we're gonna have 3 here, and 1 here, 1 here. Well, those are reactants, this is gonna be the product. For the same, here is no water, as you see, there is no water in the reactant side. Why? Because it's liquid and not unchanged. As you see, here all the coefficients are 1, so all the power up are 1. Here we have 2, so we should have 2 here. This is the reactant, this is the product. Products over reactants. And the same for these two. Okay, just one note here. If we change the temperature, the equilibrium constant will change. Changing temperature will change the value of K. Okay, great. Another examples here. As you see, here is the mercury's liquid, bye-bye, omitted out. Why? Because it's liquid. Anything liquid or solid, not included, okay? Not included directly. And always coefficients are to the power up. As you see here, we have 2, we're gonna have 2 here. Easy. Okay. Here, just a case study of hydrogen with iodine to give me hydrogen iodide. As you see, here is our reaction. Hydrogen will collide with iodine gas to form hydrogen iodide. Then hydrogen iodide will decompose to give me iodine and hydrogen gas. This is the forward reaction. As you see, there is a decrease in the rate. Here for the reverse reaction, we have increase in the rate. Then we're gonna have forward rate will equal the reverse rate, we have the equilibrium. Okay, this is the net chemical change equation for this reaction. And if we want to write K, here is the product and here is the reactant. As you see, HI to the power of 2. Why? Because we have the 2 here as a coefficient of hydrogen iodide. Here we have 1, here we have 1, since we have 1 here and 1 here. Okay, this is the value of K for this reaction. As you see, here we did 4 experiments. As you see, since there is no change in temperature, there was an average value of 54.3. Okay, the same. Okay, let's have a sample problem for us. Okay, an equilibrium mixture of N2O2 and NO2 nitrogen monoxide gases at 1500 K is determined to consist of 6.4 times 10 to the power of negative 3 mole of nitrogen. So we're gonna have nitrogen will react with O2 in equilibrium with, okay, NO, and should be what? A balanced chemical equation. So we put 2 here, and this is the concentration of each. So K will equal concentration of NO to the power of 2 over concentration of N2 times concentration of O2. Great. As you see, here's the given, the unknown is K, and here is our solution. Should be balanced chemical equation, and K will equal NO2 here over N2 times O2. With numbers, we're gonna have 1.1 times 10 to the power of negative 5. Thank you very much. Our next lesson will be about shifting equilibrium. I will send you extra practice after this session, inshallah. And let's make a small wrap up for our session here. We have 3 objectives. We started with defining the chemical equilibrium, which means there is an equal rate of forward reaction with the backward or reverse reaction, correct? And these are equal rates. This is the meaning of chemical equilibrium. Then we say there is an equilibrium constant we can obtain, which is K, and K will change with temperature. Changing temperature will change K, and we write the chemical equilibrium expression, which is K will equal the concentration of products over the concentration of reactants to the power of coefficients, which is X and Y. Thank you very much for this interesting session. I'm gonna see you inshallah next session, and I will send you all the practice, and see you inshallah. Bye bye.